Hey guys, in the last video we proved reflection of light, that is the law of reflection of light, I is equal to R, by Huygen's principle. Today in this video we're going to prove refraction with the help of Huygen's principle. If we are able to prove reflection and refraction, half of which is done, we can essentially say that the wave theory of light is absolutely right. So let's move on to the figure of this particular derivation. Let's analyze this figure. First, an incident ray I1 is coming and striking the interface of two transparent media, a rarer medium and a denser medium, in which the velocities of light are v1 and v2 respectively. Two rays I1 and I2 are incident on the interface right here. By the time I1 strikes O, I2 has only moved a distance of until A, up to A. So by the time I1 has struck O, the ray I2 has only moved up to A. The ray I1 strikes the interface, goes into the second medium and reaches the point B. And by that time I2 strikes C, that is the interface. Now if we make two wavefronts of ray I1 striking the interface and ray I2 striking the interface, we get two perpendicular lines onto the two rays of light. We also must keep in mind that wavefronts and rays are always perpendicular to each other, that is, this angle is 90 as well as this angle is 90. Great. Now by simple geometry we can say that this angle in here will be I, considering the angle of incidence to be here and the angle of refraction to be here. We can also say that the angle of refraction is the angle in here. Now moving on to the further proof. Before moving on, I'd like to say that AC is equal to v1 times t, because we know that distance equals velocity into time, and the distance AC, because of the ray is traveling the medium 1, is equal to v1 into the time. Also, in the same time t, the light moves from O to B, but in medium 2, light has a velocity of v2, and hence distance OB is equal to v2 times t. Now that all of this is said and done, moving on to the rest of the proof, where we'll have to essentially prove Snell's law, because Snell's law is a law of refraction. Sine I, that is the sine of angle of incidence, is equal to what? We're considering angle of incidence to be here in this case, so sine of angle of incidence is obviously equal to AC, opposite by hypotenuse, which is OA. Also, sine of angle of refraction is equal to OB by BC, opposite by hypotenuse, right? We can obviously say that AC is equal to V1t, and just substituting that we get sin I is equal to V1t by OA, and sin R is equal to V2t by BC. We also observe that AO is equal to BC. How is AO is equal to BC? These two lines are obviously parallel, and also they are refracted by the same angles as soon as they enter this medium. Because they are refracted by the same angles and the distance between them is absolutely the same, OA is obviously equal to BC. Because AO is equal to BC, dividing both the equations we get V1t upon OA by V2t upon OA, of which OA and OA gets cancelled out, and we get V1t over V2t, of which t and t get cancelled out, and we get V1 by V2. We must prove that sin I by sin R is equal to a constant, and since V1 over V2 is a constant, Snell's law is proved. CBSE doesn't ask you for more. If you end here, that's enough. Don't worry about N2 by N1 and those things. Okay, so proving sin I by sin R is equal to V1 by V2 is quite enough. Thank you guys for watching this video, and as usual I give you a quick snapshot of what I've done in this derivation. There you go. That's the figure, and we took angle of incidence and angle of refraction to be inside those two triangles, that is AOC and BOC, and we wrote the respective equations, took AC as B1T and OB as B2T, divided both the equations to cancel OA and T to get V1 over V2. That's it guys. So please like, share and subscribe to my channel. It's a growing channel with a lot of ambitions, so just kind of try to support me by hitting that like button, and I think that's the smallest thing you can do. Thank you guys, thank you so much.